Everybody. As Justina said, I'm Giulia Bonino from the Euro-Mediterranean Center on Climate Change. And today I will give you a brief introduction on marine extreme indicator. And then we will have two presentations on marine heatwave by Ronan and Roshin. So before going on extreme, let's talk about the framework to select an ocean indicator. So here we have the criteria for an ocean indicator. So an ocean indicator has to be verified, meaning that must represent an ocean phenomena that has a scientific rationale. This has to be significant, so must provide robust information, has to be scalable, meaning that has to be can provide information either, for example, for a global scale or a regional scale, and it can be also scale either in time, so can be a daily indicator or monthly indicator. Has to be justified, meaning that has to be understandable from a broader audience. Of course, has to rely on variables that usually has to be one of the essential variable, has to be defined in the framework of the essential variable framework, and has to be accessible, meaning that we can have access to this indicator. Just to give you an idea, an example of ocean indicator are the ocean warming, the sea level exchange, and the sea ice changes. But now, why do we need marine extreme indicators? So here, I'm showing you a map of SST anomalies during last summer. And as we can see, we have an SST anomaly from 5 to 6 degrees Celsius. And this anomaly causes really a lot of impact. For example, they impact the Benthic and the pelagic communities. They boot storm and tornadoes, and also they had economic impact for the tourism and also for the fisheries. But of course, not all the anomalies have impact on the ecosystem, let's say, on the human as well. So we have to identify which of these anomaly have an impact. So we need to pass from the temperature anomalies, for example, to an extreme indicator. And so the question is, what do we need to define a marine extreme? So since this is a training, I prepare for you a Mentimeter question. And I'm going to start the presentation here, and you have to scan this. And this is, I think, is a multi-choices question. So the question is, which of the following are needed to define a marine extreme indicator? And okay, so a lot of you is responding, but how I can explore? Okay, so it just keeps taking a bit of time. Okay, so you're a lot. Okay, so the responses were an essential ocean variable, a climatology, a threshold relative to climatology, and an impact on ecosystems. So I would say that everybody said the right response. Indeed, the only one that is actually we don't need to define properly for an extreme is an impact on ecosystems. This is a consequence. This is not what we need to define it. Indeed, if we go to the definition, here in the presentation, This is what we need in order to define an extreme. So actually, you did pretty good. So what we need to define an extreme, here we have the marine heat waves, the extreme levels, the extreme sea level, and also the sea ice loss, the extreme, of course. What we need is this that I highlighted in red. We need a variable to build our index. Then we need a climatology that could be also that can have a different temporal result frequency. And also we need a threshold that usually is based on the percentile. But this depends also on the extremes. The impact is not necessary to define an extreme, but is something that so we need the indicator to fight the impact and try to solve it. Now, since the presentation from Roshin and Ronan will be on marine heat waves, we will go in detail of the definition of the marine heat waves, and I prepare another metimeter. I will start the presentation here. Here we have 3 questions. So the first question is, which essential ocean variable is the most commonly used to define marine heat waves? So we have sea surface temperature, subsurface temperature, ocean heat content, and sea level anomaly. So it's quite easy, I think, this one. Yeah, everybody's saying the sea surface temperature. Yeah, of course, because in this question I put the most commonly used. So the sea surface temperature is the one that we use commonly. But yeah, someone is saying the subsurface temperature, and sometimes, for example, Ronan in one of his paper, he used also the ocean heat content. So yeah, let's say, first above all, we use the sea surface temperature because we have data. That's the point. We have the satellite data that are in a grid. They are quite accessible, so we can compute marine heat waves. For the subsurface temperature, we have data, but we are using reanalysis usually, most commonly. And then, of course, also for the ocean content, we have to rely on models. Then the second question, how long should the minimum length of the climatological baseline be to define a marine heat waves? So we have 10 years, 20 years, 30 years. Yeah, I think that also this question is quite easy. Yeah, okay. So, okay. The right response is 30 years. That is the definition the first definition that we had. Of course, depends on the data that you have. Usually, if you are considering reanalysis and satellite data, then we need to use at least 30 years of data. Of course, if we have some observation, maybe we have to rely in a shorter climatology, but still we need to consider the majority of study has to consider at least 30 years. Then we have the last question that is, I spoiled a bit before, anyway. What threshold is most commonly used to identify marine heat waves? Okay. So I will wait like 20 seconds maybe. Yeah. Yes, the most common use is usually the 90 percentile of acclimatology, but since we are going right warmer climate, we are starting to consider also the 95th percentile of climatology. And so, yeah, you are quite right. Okay, I will come back to my presentation. And I want just conclude saying the definition of the marine heat wave. So a marine heat wave is a prolonged, discrete, anomalously warm water event. And anomalously means that this event has to be warmer than a threshold, that usually the 90% percentile, in a 30-year baseline climatology. This definition was born in 2016 by Obde et al. So it's quite new, let's say it has just 10 years old. So I will give the floor to the other speakers, and I hope that you enjoy the presentation.
Okay, my name is Roshin, and today I will guide you through the Barents Sea marine heat waves. Yes. So in the next 10 to 15 minutes, you will see the topics listed here. I will start with the Arctic warming and zoom into the Barents Sea, and highlight the importance of the region in the Arctic. Then I will talk about the surface and deep marine heat waves in the Barents Sea, the mechanisms and drivers associated with it. Then we will focus on the different definitions of marine heat waves, like using a fixed climatology or changing the percentile from 95 to 90 and things like that, and how it impacts the marine heat wave statistics. Yeah. And finally, I have one slide on connecting marine heat waves to the coastal habitats. Okay. So we all know that the Arctic is alarmingly warming. So this picture shows the anomalies in annual sea surface air temperature in the Arctic. The time series shows that the Arctic is warming very fast during the last decades. And the Arctic has warmed nearly 4 times faster than the global average, with the maximum warming in the Barents Sea. This is the importance of the Barents Sea here. So I will, and the region in the black box, this is the Barents Sea region. So Barents Sea is the largest shelf sea that is adjacent to the Arctic Ocean, and it accounts for a substantial part of dense water that is formed in the Arctic. So can you see my cursor also? Yeah, okay. So this is the Barents Sea. We can divide, or we can think the Barents Sea as two systems, actually, the north and the south. The south is basically dominated by the Atlantic water origin, while the northern part, so the Atlantic water is usually warm, while the northern part is basically dominated by the Arctic waters, which is cold. So there are two kind of distinct definitions, distinct region in the entire Barents Sea. So the Barents Sea is very important as far as the fisheries is concerned. It does have both the pelagic and the demersal fish stocks, and it hosts a large group of marine mammals and seabirds and unique benthos communities. So in the Barents Sea, two main concerns are the Atlantification in the Barents Sea. So Atlantification is a common term that we use to denote the increased influence of Atlantic waters from the south, in the red line, from the south into the Arctic region. So Atlantification has resulted in the poleward expansion of temperate phytoplankton and boreal species. It also has resulted in the northward retreat of the Arctic marine ecosystem. So Atlantification is kind of gradually happening process. Then we have the marine heat wave. It's frequent occurrences in this region. So these are the two main concerns that we are facing in this region. So I will focus on the marine heat waves in this talk. So let's start with the surface and the deep marine heat waves in the Barents Sea. So Julia has showed this figure on the top left. So the green line is the blue line is the climatology that we usually use, the reference time period of 30 years. And the green line is the percentile. In this case, we use the 90th percentile, and the temperature, the sea surface temperature is in the black. So this is a study that we did in 2022, where we looked at the sea surface temperature of the Barents Sea to study the marine heat wave statistics. We also looked at the deep bottom temperature. So this is a model-derived data. So we studied both the surface and as well as the bottom temperature data, and categorized different surface marine heat waves and deep marine heat waves. In the study, we categorized almost 29 surface marine heat waves during the 30-year time period from 93 to 2022, and 5 deep marine heat waves. In this figure, what you see is the same color code that is shown in the extreme top left. The blue is the climatology, while the green is the threshold, and the black line is the actual temperature variability, both for the surface and deep. Okay. And what we also found was there was an increasing number of marine heat waves, both in the surface and bottom, in the entire Barents Sea, as well as different regions of the Barents Sea. So in bold, so what you see in the figure is that the trend in the hashed panels, while the surface and the bottom on the indicated by the blue and the red. So irrespective of the region, the marine heat waves in the Barents Sea are increasing. The frequency of the marine heat waves are increasing. Okay. Here is an example of the 2016 event. You see that at the surface and the bottom, it almost prolonged for 1 year time period, this marine heat wave event. This was a major event during this 2016 event. Now let us look at different mechanisms. So now you have seen the marine heat waves are increasing. Now we need to look at now I would like to show you some of the mechanism and drivers associated with it. So as I have explained earlier, in the Barents Sea, we have an inflow of Atlantic water. In this time, it is green, and an inflow of Arctic water from the east in black. So the primary source of marine heat waves in the Barents Sea is the inflow of Atlantic water. So this usually triggers the marine heat waves in the Barents Sea. In the 2016 event, it was very evident. This was the precursor of the marine heat wave event. Then the next one is the heat loss to the atmosphere. So together with the inflow of Atlantic water, heat loss plays a major role. So in 2016 event, this was another major component which acted in coherence with the inflow of Atlantic water. So when we have a less heat loss to the atmosphere, we increase the longevity of the marine heat waves in the region. But there are some other reasons as well, because in 2016 we were able to explain the marine heat wave event using the combination of inflow of Atlantic water and the heat loss. But these two events, independently or combined, cannot explain other marine heat wave events. So we looked for other reasons, and then one of them is the weakening of the Arctic inflow. So the Arctic inflow from the east is usually cold. So once it is weakened, it means that less cold waters is going into the Barents Sea and out. So this is a paper that we published in 2020 last year, and this is yet another mechanism of triggering the marine heat wave event in the Barents Sea. The final mechanism is ocean eddies. There was a paper published in 2023 which looked at the global scale, and they showed that ocean eddies can also trigger the marine heat wave events. But no study has been done yet in the Barents Sea. So we started to have a look at it. And then this is so from satellite altimetry and using satellite altimetry, sea surface height data and sea surface temperature data, we try to quantify the eddies, track or to detect and track the eddies. So usually anticyclonic eddies are warm core and cyclonic eddies are cold core. That is what we are seeing here in this figure. We have a warm core eddy and a cold core eddy. So we expect the warm core eddies to act as a major triggering mechanism for the marine heat wave events. But this is not always the case, because this is the case when we only consider the eddy pumping mechanism. So when the wind acts and Ekman eddy pumping mechanism acts, then the anticyclones and cyclones behave oppositely. As you see in the lower panel, we have a cold core anticyclonic eddies and warm core cyclonic eddies. This is due to the divergence and happening when we have an impact of the wind. This is called eddy Ekman pumping. Okay, so we need to consider both the cyclone and anticyclone in this case to study the impact of eddies on the marine heat waves. This is a simple example of choosing only the warm core anticyclonic eddies, and this is the pentard changes in the sea surface temperature of the anticyclonic eddies. You see that during the lighter period, the core of the cyclone or the anticyclones are getting warmer, which will in turn impact the marine heat wave eddy initiation. Okay, so now I have gone through the mechanisms associated with the marine heat wave events in the Barents Sea. So now let me take you to the different definitions of marine heat waves. Julia has given a brief introduction to the different criteria that we use. You have answered the questions as well. So here is a paper, or here's the data set that is part of this OpsiFoclim project that is in review now. This gives us access to the multi-definition global marine heat wave data from sea surface temperature. So in here, what we do is to provide marine heat wave statistics based on different baseline, 30-year baseline WMO, and a different reanalysis baseline, 1993 to 2016. Also different percentile, 90, 95, 99, and persistence. So usually we consider 5-day, a minimum of 5-day occurrence to categorize a marine heat wave. So this data set will be freely available for everyone to use. So today, I will show you an examples using the categories. So how using different baselines, percentiles, and persistence change the eddy statistics. So category, for those who don't know what is category 1 corresponds to anomalies that is just above this threshold. Category 2 for anomalies 2 to 3 times the threshold difference. 3 is 3 to 4 times, while 4 is above 4 times, above or equal to 4 times. Okay. Oh, so here is an example of 2016 even. So during the year 2016, this is category 1, 2, 3, 4. For the 90th percentile, 95 percentile, 99 percentile. You see, and this is for the 5-day persistence. You see the difference starting to show up. It's not the difference is quite evident when we compare the 90th percentile and 99 percentile. While it is not so, there are differences, of course, between the 90th and 95 as well. So so now we can check whether the 10-day persistence changes anything between. So I don't see a clear difference between 90th percentile, the 5 days and the 10 days. So it's basically, or the other pictures as well. So basically it's the percentile which is creating the most, the largest difference here. Okay, this is the percentile, and then we can move on to the baseline or the time period that we use. The first is the 93 to 2016, and this is the second one, or the panel to the right is the WMO baseline, 91 to 2020. You see there are differences when we use different baselines as well. Yeah. So my intent to show this figure is to show that, okay, once we use different baseline, there will be different statistics that we retrieve out of that. Okay, so this is my final slide, connecting marine heat waves to coastal habitats. So this is an example where what you see here in color is the marine heat wave, the trend, and we looked at the most susceptible regions of the coral reef and seagrass. You see that the trend is kind of high in those regions. So now, since we can monitor seagrass from satellite and using AI, that's for the next future training, how to do that. We can connect the marine heat waves to the directly to the coastal habitats. So in summary, I have taken you through a brief journey, focusing on the Arctic warming, zooming into the Barents Sea, surface and deep marine heat waves in the Barents Sea. Hope you have learned something about the physical mechanisms associated with it, and different definitions, how the marine heat wave statistics changes when we use different definitions, and an example of how to connect the marine heat waves to coastal habitat. Thank you very much.
Thanks very much, Justina and Julia and Roshan, for a great introduction and for a very nice talk on the Barents Sea. We're going to change position completely now, go further equatorward. I hope you can all see the screen.
Yes,
now we're going
all
to
good.
focus, excellent, we're going to focus on the Mediterranean Sea. Still talking about, of course, this interesting discussion of how best to define marine heat waves, but in this case we're thinking of what you need to do when you want to study a particular precursor, and taking into account different spatial and temporal scales. So indeed we're focusing on the case study of large-scale atmospheric precursors in the Mediterranean. First of all, well, let's have an overview of the different types of marine heat wave drivers. So the accumulation of heat in the ocean, it depends on processes which act on a wide range of spatial and temporal scales. In this very nice schematic from Holbrook et al. 2020, we have, sure, in the lower right, some information on the impacts on ecosystems and ocean health. But for now, let's focus on the rest of the picture. On the left, we have the, let's say, local scale drivers, the more direct drivers of heat accumulation in the ocean. Of course, above we have the role of the atmosphere. Now, typically heat extremes, even over land, the ones that we suffer from, are caused by high pressure systems, which cause a blocking of air, reduced cloud cover. They're linked to suppressed winds, and also an increase in incoming radiation. But at the same time, these high-pressure systems, and indeed with marine heat waves, we often see a reduction of the heat lost to the atmosphere, because processes like latent and sensible heat loss, evaporation, they cause a heat loss to the atmosphere, and they can be restricted during marine heat wave development. And at the same time, within the ocean itself, there's important processes such as suppressed vertical mixing, a shallowing of the mixed layer, which can really intensify the temperatures at the surface. And then you have a reduction of transport from the deeper ocean, which brings cooler water to the surface. And that, given that you have suppressed winds, is typically a suppressed or switched off completely during a marine heat wave. So these, as I say, are the local scale processes to consider. What's even more fascinating is the link to atmospheric teleconnections and to climate drivers like the El Niño Southern Oscillation. Now these, given that they act on larger spatial scales and longer time scales, there is often a lag of weeks to months. They don't directly cause, in many cases, they don't directly cause marine heat waves, but they modulate the interannual statistics of the marine heat waves, such as ENSO might bring about larger intensity or longer duration, etc. In the Mediterranean, of course, these links do exist, but they are certainly non-linear and not so obvious for extremes. So why all this discussion on the types of drivers? Well, how we define and monitor marine heat waves, in other words, our choice of definition and indicator, it can affect our understanding of drivers. That's probably a negative way of putting it. Let me put it this way. Whatever driver we want to study, we need to think carefully about how we're defining the marine heat wave. For example, you could study, as Ronan has shown, heat waves defined relative to the 90th percentile, the 95th, or the 99th. And it could be that the drivers of these different severities differ. Likewise, thinking of spatial and temporal scale, if I'm looking at local or coastal scale marine heat waves, they may have a very different set of drivers than these enormous basin scale drivers. For example, coastal upwelling has a role in the coastal zone. If we're thinking about a marine heat wave occurring across the whole North Atlantic, there will be more of an impact of some of these climate drivers and atmospheric teleconnections potentially. We need to consider that the setup of the problem, let's say, what do we want to show? And I think what I'll do now is show some examples of that. Let me zoom in quickly to the Mediterranean then. We already know a fair bit about what drives marine heat waves in the Mediterranean. This nice example from Simon et al. 2023 shows summer average statistics for marine heat wave intensity for 3 of the most intense or long-lasting marine heat waves. And on the right, we have the corresponding summer average Z500 anomalies. So that's showing where the atmospheric pressure was relatively high and where the circulation has been changed. And in all cases, we see that the summers were characterized by high pressure systems over the Mediterranean, even if on the larger nearly hemisphere scale, the patterns are quite different. So generally, we know that positive temperature anomalies are associated with high pressure, blocked air, weakened winds, and that in turn causes these changes in air-sea heat fluxes, which causes the heat to accumulate in the upper ocean. What we'd like to do now then is kind of prove systematically for all the events in the Mediterranean what the link is, not just for certain important examples, but to, as I say, prove statistically and systematically. And here's how we decided to do that. First of all, given that we were looking at large-scale drivers, so these large-scale atmospheric circulation patterns, we decided to go from local point-based marine heat waves to a kind of regional scale view of coherent structures. So what I mean here exactly is, as we've seen before a few times, you can define your marine heat wave as an exceedance of a particular threshold, and you do that for each grid point of your satellite data of your model. Then what my colleague Julia did actually, is to make a data set of these coherent structures. So she applies a statistical connectivity algorithm, which links individual marine heat waves, individual points, by their spatial and temporal similarity. So we can see here an example of this purple marine heat wave, moving, expanding, and shrinking with time. And statistically speaking, it is different from the other patches which have either appeared later or have begun in a different area of the Mediterranean. So this gives us a data set of macro events, large-scale marine heat waves. We built that, or Julia built that from the European Space Agency SST data, as I say, using this connected component analysis with quite a standard definition of marine heat waves. And then from that, what she did is extracted 3 typical patterns of marine heat waves in the Mediterranean. So this is a clustering analysis, which gives us Western Mediterranean events, as we saw a few slides ago for 2022, for example, Central Mediterranean, which extend from the Adriatic into the Ionian, and Eastern Mediterranean type events. And they all have different number of events and different intensities. That allows us to study large-scale events, which should, in principle, be easier to link to larger-scale atmospheric processes. What are these atmospheric processes I'm talking about exactly? Let's introduce some of the main candidates for the Mediterranean. We have, for example, subtropical ridges. I can hear a microphone on, by the way, so someone could close that. Thank you very much. We have subtropical ridges, which are meanders of the jet stream, so extensions of high pressure systems, which in the case of Mediterranean are often called African anticyclones, often in the media, because indeed they bring high pressure and warmer air from the northern African continent. And they extend into the mid-latitudes, causing a bending and meandering of the jet stream. Otherwise, you also have blocks. Now, subtropical ridges, if they extend very further north and become unstable, they can pinch off and separate from the rest of the atmospheric flow and cause a block, so a persistent, stuck, high-pressure system in the northern latitudes. And both of them are known to cause heat waves terrestrially. Blocking, as you can see here, is typically further north. Scandinavia, British Isles, that sort of latitude. And we actually, one of the first things we found was that in the summer in the Mediterranean, blocking is incredibly rare. So our candidate is actually the subtropical ridges. So we had to look and think, well, during these different types of Mediterranean marine heatwave events, what are the subtropical ridges doing? Are they stuck? Are they persisting? Is there some link? And so to do that, we come to kind of the final lesson in defining the marine heat wave in this study. We needed to pick a time to study the processes in the atmosphere. So here we picked the onset period. Indeed, no matter how you define a marine heat wave, you have metrics like the intensity, duration. The onset period is another important one. And here we define that as the 5-day period before the peak of the marine heat wave area. So we're really at the largest, the point of the largest extent of the marine heat wave. On the right, you can see an example of a subtropical ridge really extending far north to the British Isles and covering the whole Mediterranean. At the bottom, we can see again our clusters, the average marine heat wave intensity for each type of event, Western, Central, Eastern. And at the bottom, I'm showing here the composites during the onset period of the increase in subtropical ridge frequency during, as I say, during the onset period. And what we're seeing in that each of these events over the area of marine heat wave occurrence, we have a very strong and statistically significant increase in not just the subtropical ridge occurrence, but actually we're showing that they have to occur every day, not just every few days. So they are persistent subtropical ridges. And we're showing that when they are persisting over the Western Mediterranean, we have Western Mediterranean marine heat waves, and the same for the Central and Eastern Mediterranean. So there it was quite important to define the large-scale marine heat wave macro events and to consider this onset period. And of course, with these definitions, we do sensitivity studies and to see if there's any great sensitivity. Fortunately, in this case, not so much if you consider 5 days, 10 days, but of course, the further back you go from a marine heat wave event, the weaker the signal is for the atmosphere. That's the kind of limit of predictability. I will finish there to leave 10 minutes for questions. But some of the lessons we learned from the study, and I hope you learned too, is that there is a great flexibility in how you define a marine heat wave, which can be problematic, but is also, in my opinion, it has its positives. It means we have to define our problem well, to think about the spatial scale and the event severity. And we think we found that understanding large-scale drivers requires a regional scale definition of marine heat waves, which certainly benefits from that. And we also kind of inadvertently looked at the link between this indicator and other indicators, such as of atmospheric circulation, prevailing winds. Roshin talked about ocean transport. For more technical details and results, you can check out the paper that this talk was based on. But for now, I think I will stop and leave the floor to any questions there may be. Thank you.